So in 1897, Thomson discovered the electron by using the cathode ray tube, but his discovery of the electron only found the charge to mass ratio of the electron. That was enough. That was enough to tell us that these mysterious cathode rays were negatively charged subatomic particles. But people wanted more, not just a charge to mass ratio. What's the charge and what's the mass? Not what's the ratio of the charge to the mass. So enter Millikan a few years later, who says, I'm going to perform an experiment with a couple charged plates and some oil. The charged plates got to have a power supply hooked up to them. Doesn't really matter, to be honest, which way we hook that power supply up. We'll set it up like this in our diagram, but it could be the other way around. If we set it up like this, that makes the top plate positive and the bottom plate negative. Now, what you do here, or what Millikan would have done here, is injected microscopic droplets of oil. Oil is good because it holds a charge well. Okay, we inject these microscopic droplets of oil using what we call an atomizer. An atomizer is kind of like a perfume dispenser. Okay, you put on perfume or cologne in the morning, you spray it. It's this liquid that's inside this bottle, and it turns into not droplets of perfume or cologne the size of atoms, but still really, really, really small. That's what we're doing here. Okay, we squirt this in there, and it's not making these oil droplets the size of atoms, but they're becoming really, really, really small. Now, these oil droplets, some of them become charged. They become charged by rubbing against the nozzle of the atomizer. Some of them rub against each other, become charged. Some of them we have to irradiate actually with something like X-rays maybe to cause them to become charged. Don't worry so much about how they become charged. These oil droplets become charged. Some of them positive, some of them negative. Let's take a look at a positively charged oil droplet and a negatively charged oil droplet. Keep in mind, as you're doing this experiment, there would be hundreds or even thousands of them in this section, this compartment in the oil drop experiment. We're looking at two of them, one negative and one positive. Let's draw a free body diagram for both of them. What forces act on these charged particles? What forces act? There's two of them that act on both of them. What's one of them? Yep, gravity. Now, gravity, interestingly, in the cathode ray tube, nobody asked me about gravity. Doesn't gravity act on these? When the charged particles went undeflected through the velocity selection chamber, and we said Fe equals Fm, isn't there a force of gravity in there? Yes, there is. Why didn't we pay attention to it? Because the force of gravity on electrons is so ridiculously small compared to the electric and magnetic force, it just wasn't important. It was there, but it wasn't important. Here we're talking about oil drops, not electrons. Oil drops have a mass that's much more significant than the mass of a single electron. So now the force of gravity becomes more significant. Okay? Fg is acting down on both of them. What other force acts? Magnetic force? No magnetic force here. There's nothing to cause a magnetic force. What other force, Rucker? The electric force. The electric force acting on the negative is upwards, and the electric force acting on the positive would be downwards. Now, we don't know the values of those, so we don't know how long to draw the forces. That's okay. Don't worry about the magnitudes right now. Now, there's a couple of things that can happen to these particles. Number one, they can accelerate. They could accelerate either up or down. This guy, we know for sure the positive charge is going to accelerate downward. You got two forces acting down, it's going to accelerate downward at a rate that's greater than 9.81 meters per second. Okay, we know that for sure. But the first one, the negatively charged particle, could accelerate downward if Fg is bigger than Fe, but it could accelerate upward if the electric force is bigger. It could go at a constant speed, or it could be suspended. It could just stay there if the force is balanced. What we want to do first is examine the oil droplets that are suspended or moving at a constant speed. So in other words, we don't want to pay attention to this positive right now. We'll take a look at that later on. Okay, right now we want to take a look at this negative, and specifically this negative when these forces balance. What's going to happen when these forces are balanced? It's going to be suspended, or it's going to travel at a constant speed. Okay, either one. If it's not moving, it's going to stay not moving. If it's moving, it's going to stay moving at a constant speed. For suspended oil drops, or those that are traveling at a constant speed, we're going to say that the upward electric force is equal to the downward force of gravity. Now, don't get that mixed up with the velocity selection chamber where Fe was equal to Fm. Okay, don't memorize that. Okay, look at the velocity selection chamber and think, okay, we got parallel plates, we got a magnetic field. Fe equals Fm. There's no Fm here because there's no magnetic field. The electric field is Q times E, and the gravitational force is M times G. Rearrange this, get Q is equal to mg over E. The charge of, what are we solving for here? The charge of, remember the point of this? Go back to the beginning. Thomson found the charge to mass ratio of an electron. Millikan wanted to find the charge of an electron. What's he solving for here? No, he's not solving for the charge of an electron here. He wants that, but that's not what he's got right now. This is the charge of an oil drop, not the charge of an electron. But guess what happens? When he solves for the charge of an oil drop, he gets a number that's maybe 3.2 times 10 to the minus 17 coulombs. Or maybe he gets another one that's 9.6 times 10 to the minus 19 coulombs. Or he gets another one that's 1.6 times 10 to the minus 18 coulombs. Or he gets another one that's 1.6 times 10 to the minus 19 coulombs. Or 4.8 times 10 to the minus 17 coulombs. He repeats this maybe hundreds of times. And when he does, he finds that all 200 charges of oil drops that he found are multiples of that. They're all multiples of that charge. 1.6, hey, look at this. This is 300 times this. This is 10 times this. This is what? 4 times this. This is 200 times this. They're all whole number multiples of that. So now Millikan concluded 2 things from that. Number 1, there is an elementary charge. What does that mean? Well, it means that there is a charge that is the smallest possible charge you can have. You can't get any smaller. Its value is 1.6 times 10 to the minus 19 coulombs. Remember way back in Unit 2 when we said, look, here's how you find the charge of an electron or the charge of the alpha particle on your data sheet. Remember I said you go to the left-hand side and you see the elementary charge is 1.6, and then you multiply it by however many elementary charges the alpha particle was. Okay? That's what we're talking about here, the elementary charge, the smallest possible charge. He concluded that because, look, after repeating this a few hundred times, if they're all multiples of this, and he didn't get anything smaller than that, then he's saying, well, you probably can't get anything smaller than that then. That's as small as you can get. The elementary charge is 1.6 times 10 to the minus 19, and, would you look at this? Since an electron is a fundamental subatomic particle, that must be the charge of an electron. Look at that. He's just found the charge of an electron. Now, the other thing that he concluded from this was that charge is quantized. And what that means is that you can have the elementary charge Or you can have a multiple of that, but nothing in between. It's kind of like people are quantized. You can have one person, or you can have a whole number multiple of one person, 7 people, 25 people. You can't have 3.9 people. Point taken. You can have 3 people or 4 people or 2 people, but in most cases you can't have 2.5 men. Stairs. Walk upstairs. Okay, your energy is quantized, right? If you have 100 joules on the first step, well, you can have 200 joules on the second step or 300 joules on the third step. You can't have anything in between. Money is quantized. You can have 5 cents, or you can have 10 cents, or you can have 15 cents. You can have a nickel or a whole number multiple of nickels. Okay, he's saying charge is quantized. You can have 1.6 times 10 to the minus 19, or twice that, or 463 times that. But you can't have 9.6 times that. So there's an elementary charge which corresponds to the charge of an electron, and charge is quantized. Now, take you back here for 1 second. Is it that easy? That easy to solve for a charge? When I was in university, and in my 3rd year, I had this course, 6 hours of physics lab per week. That was it, just lab, 6 hours physics lab per week. At least that's what it was theoretically supposed to be. Sometimes it worked out to be 3. Sometimes it worked out to be 12. But it was supposed to be 6 hours a week. I did this experiment. It is, let me tell you, it is the most, for me at least, it was the most miserable experience of my life. Okay, almost. It is messy. It is difficult. It takes a long time. Okay, it's not as simple as I've made it out to be here today in practice. Okay, in the end, it looks pretty easy, right? But it's difficult to get the oil droplets balanced. It's difficult to see the oil droplets. The reality is you're looking at this thing through a little mini telescope so that you can see these microscopic oil droplets. Okay, how do you find the mass? Well, basically, it's an analysis of the size of the oil drop. You measure the size of the oil drop, and then you know the density of the oil. And then from the size and the density, you can find the mass of it that way. Okay, it's harder than I'm making it out to be here. It's much harder than I'm making it out to be here. But the basic principles are there. Okay, the basic principles are, look, if you can find the mass, and you know G, and you know E, you can find the charge of an oil drop. And when you do, they will be either 1.6 or a multiple of 1.6. And you can conclude this. All right? Let's take a look at an example, okay? 15.3 on 763, it says, an oil drop of this mass is suspended. Good. If it says it's suspended, or if it says it's traveling at a constant speed, either one of those, then doesn't matter. We're going to say Fe equals Fg. Now, we want to find the number of electrons the oil drop has gained or lost. We're not going to worry about that right now. Let's get a charge. Okay, we're going to say Q times E is equal to M times G, and we're going to solve for Q. It's mg over E. The mass of the oil drop is 8.2 times 10 to the negative 15 kilograms times 9.81. The electric field strength is 1 times 10 to the 5. Let's get the value of the charge there. Remember, not of an electron, the charge of that oil drop. We get 8.04 times 10 to the minus 19. You guys remember how to find a number of electrons? This is way back to Unit 2, right? Yeah. Not the total mass, but the total charge, right? So we're going to say the number of electrons is 8.04 times 10 to the minus 19 divided by the charge of 1 electron. And when we do that, it's going to round to be 5 electrons, a whole number of electrons. Okay. Now, is it gained or lost? Ooh. In other words, is this oil drop positive or negative? When you want to deal with that, draw a picture. Okay, it might seem silly right now. Why would you draw a picture? Okay, trust me on this right now. Draw a picture. We have an electric field that's downward. An electric field that's downward. We know that we have a force of gravity downward on this particle, and therefore we must have an electric force upward. Okay, it can't be suspended if those two forces aren't in opposite directions. With me so far? If the electric force is upward, but the electric field is downward, what kind of particle is this, positive or negative? What's the charge on the oil drop? Positive 8.4 or negative 8.4? Yep, negative. Because negative charges experience a force opposite to the field. Does that make sense? If they had said the field was upward, then we would know that this is a positive charge because the force would be in the same direction as the field. So that means that it's a negative charge. That means it's gained 5 electrons to make it a negative charge. Got that? I'm going to give you just a couple minutes to work on these questions on page 763. Then we're going to do one more example today, and then that's going to be it, okay? All right, let's take a look at what happens when these charged particles now, these oil droplets, aren't suspended or aren't traveling at a constant speed. This time they're accelerating. So maybe now we're taking a look at this oil droplet right here that was accelerating downward as a result of two forces downward. Or maybe we're taking a look at this one where one of the forces is bigger than the other. It doesn't matter. It's not suspended. It's not traveling at a constant velocity. It's accelerating. Now, if it's accelerating, we're going to do what we did back in physics 20, whenever we had a couple forces causing something to accelerate. We're going to say F net is equal to the sum of the forces. But the sum of the forces in this case would be Fe plus Fg, the electric force plus the gravitational force. Now, the net force will be m times a, just like it was back in physics 20. Fe will be q times e, and Fg will be m times g. Now, at this point, you're going to plug some numbers in, and you got to worry about signs. So if it's accelerating downward, make sure a is a negative value. Gravity will always be a negative value because it's always going to be acting down. The electric force, well, look at the situation. It could be negative or positive. In this case, the electric force would be positive. In this case, the electric force would be negative. Okay, draw your picture, and then look at whether the electric force should be positive or negative based on that picture. And then when you go to plug in the numbers, make sure you plug in whether it should be a positive or a negative value. Okay? When all is said and done, you're likely going to end up solving for Q again. And when you solve for Q again, guess what you're going to get? 1.6 times 10 to the minus 19, or a whole number multiple of 1.6 times 10 to the minus 19, indicating the exact same thing that Millikan found with the suspended / constant velocity oil drops. There is an elementary charge which corresponds to the charge of an electron, and charge is quantized. Let's take a look at this one. This one says a tiny plastic sphere. They make these latex spheres or plastic spheres now that you can use in this experiment, which makes it way less messy. Yeah, I don't know why I never did that. Used plastic or latex when I was in university and did this experiment, but a lot easier to do it now. Still, not easy, but easier for sure. This tiny plastic sphere has this mass that's placed in an electric field of this value that's downward within a vacuum chamber. It has 10 excess electrons. Is the sphere going to accelerate? And if so, in which direction? Let's draw a picture, because it's a bit confusing. We have an electric field that's downward. and its value is 1 times 10 to the 5 newtons per coulomb. We have a sphere with 10 excess electrons, so it's negative, and its charge is going to be negative 1.6 times 10 to the minus 18 coulombs, because it has 10 extra electrons on it, right? 10 times the charge of an electron. We know we have a force of gravity acting on this oil droplet, or on this sphere. And we know we have an electric force acting which way? This is why we want the picture, right? Which way does the electric force act? This is important, because if you get the wrong direction, you're going to get the wrong answer for A. Yep. The electric force is going to be upwards. Now, how big it is, we don't know, but we know it's upward because it's a negative charge experiences a force opposite to the electric field. Okay, that's been a long time now. That was back in March that we were talking about that, right? Negative particles experience a force opposite to the field. All right, let's do what we did when I was explaining this. F net is equal to the sum of the forces, Fe plus Fg. Ma is equal to QE plus mg. The mass is 8.2 times 10 to the minus 15. We don't know the acceleration. Okay, that's really what we're trying to find. Does it accelerate? Well, let's find A. If the answer is yes, it accelerates, we'll get a value for A. If it's no, then A will be 0. Okay, let's find A. Q is 1.6 times 10 to the minus 18 times the electric field of 1 times 10 to the 5 plus force of gravity, 8.2 times 10 to the negative 15 times 9.81. Okay, let's worry about signs now. We're trying to find A, so we're not going to worry about whether it's positive or negative. The gravitational force is downward, so we'll make it negative. What about the electric force? You look at the picture, right? Which way is the electric force? Caitlin, which way is the electric force here in this picture? Upwards. So we're going to leave it positive. Okay, do you understand why that diagram is so important? You don't draw that picture and you're going to have no idea whether this electric force is upwards or downwards. Okay, and that's going to make all the difference in the world for this problem. Okay, let's get the value of this now. The value of A. If there is a value. We're going to say 1.6 times 10 to the minus 18, not 10 to the minus 19, times 1 times 10 to the 5. We're going to subtract from that 8.2 times 10 to the minus 15 times 9.81. Okay, that gives me the right-hand side. Now we're going to divide that number by 8.2 times 10 to the minus 15. And that gives us acceleration of 9.71, 9.70. Or we're just going to round it to 2 digits. Solve for that, we got a positive value. What does that tell us? Positive value means, yeah, the acceleration is upward, right? It accelerates in the positive direction or upwards, so it's going up. It means the electric force is bigger than the gravitational force. Yep. Did I count for gravitational force? Yep. Right, 8.2 times 10 to the minus 15 times 9.81, right? Did I not punch it in the calculator? Yeah, I did. Right here, Ricker. See that? Makes sense? Does anybody else get that number? Okay, we'll trust that it's right then. All right, 2 more questions on 764. So your homework tonight is, if you haven't finished them already, you got the questions on 763, 2 questions. In addition, now these 2 questions on 764. Listen, don't try to take shortcuts, please. It's only 4 questions. Draw the picture. Okay, when you're trying to find out the number of excess electrons or whether it's electrons gained or lost or which way does the field go or whatever, guys, it is so important to have that picture drawn. Okay, it makes it so much easier. And if you're trying to take a shortcut, make life easier for you, okay, it's not going to. Okay, draw the picture and do it the longer way because it'll end up being shorter in the end.